In this lesson, we are going to describe the end behavior of the graph of our polynomial function using limits, and then explain our reasoning using the leading term test. It doesn't say anywhere in the directions we need to graph, but we do need to be able to look at the equation and determine what is happening to our graph on each end. What that means is if you were to look at your graph of any polynomial, it's going to typically bounce up and down sort of in the middle. It's going to be nice and smooth curves, but eventually if you go out to the left or out to the right far enough, the graph is going to go up for forever or it's going to go down for forever. So what we want to do is we want to know how can we look at the equation to describe what that looks like, and that process is called the leading term test. So for our function here, I'm going to apply these directions to f of x is equal to 3x to the fourth plus x cubed plus 5x squared plus x minus 7. So we don't have to graph this. We don't have to go through and graph this whole entire equation, but what we do need to do is we just need to describe what is happening on the left and the right sides. If it just said to describe the end behavior, we would be able to do that in words. In the Algebra 2 book that we use, it uses a combination of words and math phrases, and math symbols rather. It uses a combination of phrases and math symbols. Words and math symbols. And then for this class, we're going to look at how to do that using limits. To make that bridge, I'm going to do that with all three of these. I'm going to write the end behavior out in words, and then I'm going to write it out with a combination of words and math symbols like the Algebra 2 book does, and then finally we will write it using limits, which for most people is a new notation. But before we can do that, we need to know what the graph looks like, and that's where the leading term test comes in. So your leading term is going to be typically this first term. It will be if your equation is written in standard form. So if there are no parentheses here, and your equation has been written so the highest power of x is the first term, that tells us that that is the leading term. So sometimes they'll mix these up. This one is in standard form, the highest power of x is here, and this leading term is the 3x to the fourth. In terms of the left and the right sides with the end behavior, this is the term that we can use to tell us what's happening on the far left and the far right sides. The rest of this, all the rest of these terms, they do influence the graph, but we don't need to look at those terms in order to determine what happens on the left and the right sides. And best news of all is we don't have to graph this. We just need to look at this lead term, this 3x to the fourth, and that will tell us what our graph is doing. Let me draw a quick little sketch of what our graph might look like over here using the leading term test. Here's what you should do every time using the leading term test. You should take a look at all the terms that you have, identify what the leading term is. Our highest power of x is x to the fourth, so this 3x to the fourth term is the leading term. Then from there, you're going to be able to predict, using that leading term, if the right side of our graph goes upward or if the right side of our graph goes downward. We need to do the right side first. So let's see if our graph is going upward or downward. To do that, you look at your leading term and you look at the coefficient, the number in front. If the coefficient is positive, then your graph is going to go upward this way. So if the coefficient is positive, then your graph will go upwards over on the right side. If the coefficient in front is negative, then your graph is going to go downward. In this particular problem, our lead term is a 3x to the fourth, and the coefficient, the number in front, is a positive number. It's a positive 3. So I know the right side of our graph is going to go upward. So I'm going to erase this other piece. If this had been a negative number in front, then the graph would be going downward on the right. The left side. The left side also either goes upward or downward, and we can predict what the left side does also based on this lead term. And how you do that is you look at the exponent. The exponent in this problem is 4. If you have an even exponent, the left and the right sides have to do the same thing, just like a parabola. In a parabola, the left and the right sides either both go up, or if it's reflected, they both go down. Same thing with any even power. The whole even family is going to essentially look like that. The left and the right sides are going to go the same direction. We know the right side goes upward because the lead coefficient was positive, and because the exponent is even, I know the left and the right sides have to match. And since the right side is going up, for this problem, the left side is also going up. And again, how I know that is that the exponent is even. If the exponent were odd, then the left side would have to go the opposite direction. So that is what our graph would look like. If we were going to go through and graph this, the left side and the right side would be up. In between, this graph would be bouncing up and down, nice smooth shapes. But eventually, as you go from left to right, it would start at the top of the graph, and it would go down and maybe bounce up and down a few times, and then eventually go upwards over on the right side. If we were going to graph this, we could make an XY table, come up with a nice accurate graph. But we just have to describe what is happening on the far left and the far right side. And we do that using the leading term. Do the right side first. The coefficient will tell you what happens there. And then do the left side, which will either match the right side or go the opposite direction, and the exponent will tell you that on that one. Okay, so this is what's happening in the graph. Both the left side and the right sides are going up. Let me first go through and tell you essentially what it was that I just said, but write it down instead. In this graph, the left side of our graph goes up, and the right side of our graph goes up. The left side goes up and the right side goes up. If it just said to describe the end behavior, you could use words, and you could use those two phrases, and that would be totally fine. In the Algebra 2 book, they use a combination of these words and also math symbols. So in the Algebra 2 book, they would do this. Instead of saying the left side, they would say what happens with x when you go that direction. So as x approaches negative infinity, that's how they would, that is not infinity, there we go. As x approaches negative infinity, that's how they would start this. That says we are going over to the left. If you think about it, your x-axis goes left and right. If x is getting really, really big, if x is going to positive infinity, then we're looking at the right side of the graph. As x approaches positive infinity, we'd be going to the right for forever. If we're approaching negative infinity, we would be going to the left. So when we say that the left side goes up, if we want to describe what we mean by the left side using some math ideas, we would say as x approaches negative infinity. And now we need to say that the graph goes up. Our variable that we use to determine up and down is y. And if the graph is going up, that means our y values are getting really, really big. So the y coordinates here would be getting larger and larger and larger, and it would go up for forever. So what we could say is that f of x is equal to infinity. That would be the same thing as saying the left side of our graph goes up. As x approaches negative infinity, f of x equals positive infinity. As you go to the left, the graph goes up. Similarly with the right side. If you're going to say we're going over to the right, that is when x is getting really, really big. So you could say as x approaches positive infinity. That says as you go to the right, as x approaches positive infinity. Well, what's happening in this graph is that our graph is going up. As we go to the right, it goes up. As x approaches positive infinity, as we go to the right, our y values keep getting bigger and bigger and bigger, going all the way up for forever. So if you're going to say that the left and the right side of our graph go up, you could just use words. You could use a combination of math symbols and words. Or if they say to use limits, what the directions do here, then you need to use something called limit notation, and that looks like this. Math people tend to abbreviate words. The word limit isn't a super long word, but math people don't write down the whole word when they use it. They just write down LIM. And if you're writing it by hand, a lot of people put that into cursive. So LIM would look like this. This phrase, as x approaches negative infinity, that does tell us we're going to the left. A math person does not want to use the word approaches and write that out every time, so math people have a symbol for that. As x approaches negative infinity, the symbol that they use to replace the word approaches is an arrow. And where that goes is underneath limit. So on your notebook paper, you would write LIM right on your line, and then down below that, as x approaches negative infinity, would look like this. We would do an arrow, x, and then an arrow, and then negative infinity. And that would tell anyone that you are going to the left. That looks a little weird because the arrow actually goes to the right, but that's not what we're saying. The arrow does not indicate the direction. You have to look at what's happening. And in this problem, x is approaching negative infinity. Your x determines your left and your right, and if x is approaching negative infinity, we're going to the left. All right, so this says we are going to the left. And then we want to say our graph is going up. And we use the same notation here. F of x, which is our y value, equals infinity. That means the graph is going up for forever. And where that goes is that goes back on the line of your notebook paper along the same line with limit. So your final answer, to describe the end behavior using limits, we would do the limit on the line, and then underneath it, as x approaches negative infinity using this notation, our graph goes up. F of x is equal to infinity. Doing the same thing with the other phrase here. Each one of these is going to be a limit. Underneath here, we are going to replace the word approaches from this phrase with an arrow again, and this time we are going to the right. So x is approaching positive infinity this time. And what's happening is the graph is going up. So in the directions to this problem, it said, describe the end behavior using limits. If we could use just words, if we could use a combination of words and math symbols, these first two lines are what we would do to describe the left and the right sides. But we were supposed to use limits. So this is what your answer should look like. The last part of the directions up at the top there, you can still see it. It says, explain your reasoning using the leading term test. Well, we talked through that and we explained all of that. We knew that the right side went up because the coefficient was positive, and we knew that the left side went up because we had an even exponent and it had to match the right. So you're supposed to explain your reasoning. You could say that you know that your right side goes upward because you have a coefficient that is positive, and you can say that you know that the left side goes upward because we have an even exponent, and it has to match the right side. So your final answer doesn't require any work really to be shown. If you know the leading term test, you should be able to look at the equation. You could think about what this graph looks like in your head, and then put that into limit notation to come up with your final answer.